Hello, class. My voice is going to be horrible for this video, but I will at least get through the material for you guys. Alright, I gave you guys 2 practice tests for midterm 2, and I'll be going over both. I will be using this page over here as the cover page for the exam. So note where all the equations are and what's accessible to you because of those equations. I do plan on changing this equation right here to be b is equal to mu naught I over 2 pi r instead. It was useful for something in these exams, but I ended up not doing a question of that style of equation for you guys. Alright. Run through these. Okay, some of these are based off of videos that you can see on the Canvas page, which I didn't go over in lecture, but I'll mention when that's the case. Geophysicists today generally attribute the existence of Earth's magnetic field to which of the following? Okay, so in general, we're looking for something that has a moving charge in a circle. Okay, and iron ore deposits in the crust, don't follow that. Nickel iron deposits in the crust, don't do that. Solar flares, those are just sending charges our way. They don't actually create a magnetic field. They interact with the pre-existing magnetic field. Okay, so it's the convection currents, the circling of liquid metals in the core of the Earth. A. Next. Assume that a uniform magnetic field is directed into the page. Assumed. If an electron is released with initial velocity directed from the bottom edge to the top edge, which of the following best describes the direction of the resultant force acting on the electron? Well, my hand looks like this when I do this, meaning that my palm is pointing into the page, fingers are pointing up the page, and that tells me that I should expect a force to the left, which would be correct if we were dealing with a positive charge. We're not. We're dealing with an electron, so I flip it from being left to right. Next. 3. Which of the following statements is not true about magnetic levitation, the type that utilizes the Meissner effect? This was a video that we did not do this semester, okay? But it's B. Flex pinning. The video does include flex pinning. Works best with supercooled diamagnets. That's just something that we didn't go over this semester, but it's not a major concept. Number 4. There is a current I flowing in a clockwise direction, already drawn, in a square loop of wire that is in the plane of the paper. If the magnetic field B is towards the right, and if each side of the loop has length L, then the net magnetic force acting on the loop is, well, this side is feeling no force because it's parallel. Again, parallel, no force. Actually, instead of putting X's, which might be confused as into the page, there we go, F equals 0. On the left, the right-hand rule is getting me a force that is into the page. And on the right, I'm getting a force that is out of the page. And they are in equal measure. Therefore, the net magnetic force will be 0. Number 5. 2. Insulated current carrying wires of equal length are arranged in the lab so that wire A carries current northward, whereas current B carries current eastward. Eastward. The wires crossing at their midpoints, separated only by their insulation. Which of the following statements are true? We've done this specific one in class already, so we know that the net force is 0. Okay, so can't be A, can't be B. There are forces though, okay? For example, A creates a magnetic field that is out of the page here and into the page here, which causes forces that are up the page there and down the page there. So there are forces, and those forces end up causing torques. So are there no forces? False. There are forces, but the net force on each wire is 0. D. Six. This one's kind of just a weird math problem. I actually stopped doing this problem a few years ago. A coil is placed in a magnetic field and has a magnetic flux through it. The coil is stressed so that its area reduces to 75% of its original value. So A final is equal to 3/4 of A initial. If the plane of the coil stays the same and the magnetic flux through it remains the same, how must the magnetic field change? So BI AI is equal to B final A final. This is saying that the flux stays the same. And then replace A final with this. A initial cancels. Solve for B final. And I get 4/3 B initial, which is an increase of 33%. Done. 7. Lenz's law, which is a qualitative description of Faraday's law. According to Lenz's law, the direction of an induced current in a conductor will be that which tends to produce which of the following effects? D. This is why induction is good at braking. And by braking, I mean like in a car, slowing things down. It is opposing the effect that produces it. So if you got motion, it stops the motion. It opposes it. Okay. Whew. Conceptual questions. Design an AC generator that only puts out positive voltages. That's something that I used to cover and I haven't this semester. Describe how a constant magnetic field can be used to produce AC voltages. Use a waterfall to provide any necessary kinetic energy for the system. All right. Waterfall. A waterfall can be used to make a turbine spin. Now that it's spinning, we'll connect it with a bunch of stuff, axles and gears and whatnot. And we'll use that to make a little bit of wire spin in a loop where you got a north pole and a south pole in there, and then there's leads coming off from there. So this is spinning, and that's connected to circuitry out here, including a resistor or something. And that is an AC generator. Okay? AC generators are when you're spinning loops of current inside of a magnetic field. That generates, that kinetic energy gets converted into electrical energy. Next. 3. A snowboarder is using ungrounded copper rails curved into a U to grind down a hillside. There's my U. There's a snowboard. Person standing on it. And they're grinding both rails at the same time, so they're moving in this direction. The bottom of the board is conductive and has electrical contact to his board at both feet. The Earth's magnetic field points in the same direction as the U's area vector. Cool. This direction is possible in the southern hemisphere. In the northern hemisphere, it'd have to be into the page. All right. Does current flow? Well, here's the thing. This can cause an EMF. How can this cause an EMF? Because you're having a change in magnetic flux with respect to change in time. Now, the magnetic field's not changing, and you only have one loop. But you're changing the area. That leads to BLV, where this width is L. How much voltage are we talking about, though? The magnetic field of the Earth is about 10 to the negative 5 Tesla. Small. The length of a snowboard is about 1 meter. And the fastest I could ever picture someone going is 10 meters in a second. More likely 1 meter per second. Multiply this up, and we got 10 to the negative 4 volts. That's minuscule. So, does current flow? Yes. If not, why not? If so, why? Because induction. Due to a change in area. And is he in danger of electrocuting himself? No. 0.4 volts is not going to do anything. Or 10 negative 4 volts is not going to do anything. There we go. During an aurora event, is there a specific location that charged particles are likely to end up on the globe? Yes, the poles. In fact, I did this in class, and charges that come in like this will end up here. Charges that come in like this will end up here. And charges that come in at the center will undergo circular motion right there. So we get the aurora borealis up here, and the aurora australis down here, and we get the I'm forgetting the name offhand right now, but then one more region in orbit. Okay, does this change the net? Does this change the net charge distribution on the surface of the Earth? No. Because an electron would go in this direction, and a proton would also go in this direction. They would just go in opposite helix patterns. So, the net charge at either location will not change. All right, this one. This one uses equation I told you we're not going to have to worry about. So I'm just going to cross this one out. The cool thing about this one is coaxial cables. They create magnetic field in the core of them. They create magnetic field in this region. But out here, because the total current will be these currents into the page and this current out of the page, will add to 0. So the magnetic field outside of the cables is 0. Right, so that's a neat thing for this one. This is not we did not do the Biot-Savart law. It's just another way of saying that current creates magnetic field in a way that it wasn't going to be helpful for us. So we end up with this for our graph in the end. All right. Don't worry about that page. That's not a topic I'll have you guys do. This exam is a little bit closer to what I've been doing more recently. This one's from 2019. 3. There is a current flowing in a clockwise direction in a square loop of wire that is in the plane of the paper. If the magnetic field B is out of the page and through the loop perfectly, and if each side of the loop has length L, then the net torque acting on the loop is... Well, this loop creates its own magnetic field that's into the page. The magnetic field of the loop and the magnetic field exterior are parallel. And as long as they're perfectly parallel, they create no torque. B loop is parallel to B external. 4. 2 insulated current carrying straight wires of equal length are arranged in a lab so that wire A and wire B carry current in the same direction. Ooh, we have a quick answer for this one. We know that when they carry current in the same direction, they attract each other. Okay. Oh, that's one of the answers. Boom. Done. That's it. That's the only one. Number 5. A coil is placed in a magnetic field and has a magnetic flux through it. The coil is stressed so that its area increases by 50% of its original value. This is very similar to the other one I did. So, increases. Yeah. So area final is equal to 3/2 of area initial. So BA initial equals BA final. Final is 3/2 A initial. Area initials cancel. So B final will equal 2/3 of B initial. So it must decrease by 1/3. Boom. Keep it going. 6. Soft iron has atoms that rotate independently of each other. That's true. Hard iron is more rigid and large clumps of iron rotate together. Which one is the better material to use for an inexpensive compass? Well, what does a compass need to do? It needs to rotate with the external magnetic field. Large clumps of iron rotate together. That's a compass. Therefore, hard iron. Soft iron is good for magnetic coupling. So in the transformer lab, that's soft iron that was best to use to couple the magnetic field between two solenoids. Seven, the resistor's voltage in an AC RLC circuit. Does it lead the input voltage? Maybe. Lag the input voltage? Maybe. May lead or lag the input voltage depending on multiple factors? Yes. Because the input voltage could point up-ish, down-ish, right-ish. There were a bunch of options for the input voltage. That's the voltage of the power supply, by the way. 8. The resistor's voltage in an AC RLC circuit. Oh, it's the same setup, but it's different questions. Instead of voltage, it's asking about the current. Well, the current is pointing in the same direction as the current. It's in phase. Boom. 9, this is where a question that you guys would not get on the exam because I never gave you guys equations to use for AC circuits. But here's how it works out. We have a 100 ohm resistor. We have a 50 ohm inductive reactance and a 20 ohm capacitive reactance, leaving us with $30 there. So this angle here will be the inverse tangent of opposite, which is 30, over adjacent, which is 100. Which is, I forget offhand. I think it's the 16. Double checking on my calculator really quick. Calculator inverse tangent of 0.3 in degrees. Yep, 16.699 D. I will definitely be masked up when I come to class on Monday. Ugh. Keeping it going. I'm trying to. 10. In the following figure, a conductive bar is sliding to the right while a magnetic field points out of the paper. What is the direction of the induced current? The induced current will be in the direction of the force that the protons would feel here. So we have velocity to the right, fingers to the right, magnetic field out of the page, boom, and I end up with my thumb pointing downwards when I do that. So that magnetic force pushes the current, the induced current. And that gives us clockwise. Okay. There's another way of doing this problem, which is to say that the with the area getting bigger, we need something that will give an opposing magnetic field, and this current like that would create an induced magnetic field that's into the page, which would be in response to the out of the page, increasing magnetic field and flux. 10. A square loop of wires is moving to the right while entirely inside the magnetic field. Okay, so the magnetic field does not change. And it's completely inside, so its area, that's how much is inside of there, is not changing. And the angle isn't changing. Therefore, see, no current will flow. This is similar to the warm-up we did, where you have this thing swinging back and forth. this thing spinning, and this last one bouncing up and down. If this first one and the third one always stay inside the magnetic field and the orientations of their loops stay the same, no induced. Whereas for the middle one, you get a change in theta. So B is not changing, A is not changing, but theta is. And that one gets induction. There we go. Conceptual question. How is magnetic induction important for creating an AC generator? Well, an AC generator, it takes kinetic energy and turns it into electrical energy. And it does this using induction. It does this by having a loop of current, loop of wire, where either the magnetic field going through it changes very rapidly, the area changes, or the angle changes. Usually it's the angle, and they do this by spinning it. Okay, and that spinning is your kinetic energy rotational. So, vary. So it is the induction is the mechanism for converting the kinetic energy into electrical energy. When I first gave this exam, students had trouble with this one. And I kind of like this question too. Two long wires have current running through them. They are separated by a distance of 3 centimeters. The wire on the left is 2 amps. The wire on the right, 4 amps. Are there any locations where the magnetic field is 0? Well, this guy creates a magnetic field that is into the board here, out of the board here, and weak, and out of the board there. The 2A creates into the board, out of the board, and weak and into the board. So it's possible here. But where? I put 3 question marks there to say where exactly are we talking about? Well, the magnetic field near a line of thing is mu naught I over 2 pi r. So I've got 2 sources pointing in opposite directions. Mu naught I1 over 2 pi r equals negative. I'll just do absolute value. Mu naught I2 divided by 2 pi 3 minus r. Lots going to cancel. Mu naughts cancel. 2 pi's cancel. Okay. And I can say I1, which is 2. I2 is 4. And I get that 3 minus r times 2 is equal to 4 times r. I did that by multiplying this up and multiplying that up. Multiplying this out, I get 6 minus 2r is equal to 4r. 6 is equal to 6r. R is equal to 1 centimeter. So where? It's approximately here. Where this is 1 centimeter and this is 2 centimeters. Everywhere along here, B total is equal to 0. Because the two sources cancel out. There we go. It can't happen over there because same direction, they'll add together. Over here, same direction, they'll add together. Only in the middle can they cancel out. 3. Magnetic braking occurs when a copper pendulum swings between the north and south poles of a magnet. I think that's a typo. But less so when there are slits cut in the copper disc of the pendulum. Describe why this breaking occurs and why the effect is less so for the cut copper. Okay, so this is induction. Magnetic induction, which requires a change in either magnetic field, area, or angle. When you have a smaller area because of the cuts, leads to smaller effect. Done. That's it. Keep it simple. What three properties can be changed to produce an EMF? B, A, theta. Show an example of each of these changes occurring. This one would be like we have a solenoid and you move a magnet nearby it. Okay. The area one, when you move the bar. And theta, AC generators. Done. Almost done. 5. At resonance in an AC circuit, reactances of the inductor and the capacitor cancel. Why does this result in a larger power output by the resistor? Because the current and the voltage inputs maximize at the same time. Short answer. What is the direction of the magnetic force on each part of the wire? A and C. F is 0. Because parallel. The magnetic field is parallel with the current. Whereas for B, right-hand rule, I end up with the force being into the page. Seven. This is exactly like the one on the first page. And not like copy and pasted accidentally. So, no current. 8. A uniform constant magnetic field does no work on point charges moving through it. Why is that? Because when you have a uniform magnetic field, and you have a charge moving through it, it feels a force. It's perpendicular to the motion. When the force is perpendicular to the motion, the force is also perpendicular to delta x, and work is equal to F parallel with delta x. which is by definition 0. All right. Number 9. What are the 3 shapes of paths that an electron can make when traveling through a magnetic field? If the velocity is parallel with the magnetic field, F is equal to 0, and you get straight line motion, no deviation. So it's linear. If the velocity is perpendicular to the magnetic field, then the force causes circular motion because the force is perpendicular to the velocity. So, circular. Lastly, if the velocity is at any other angle relative to the magnetic field, then you get a combination of linear and circular motion. Helical motion. And that's it. All right. Hopefully this helps you guys study. Remember that there will also be a resistor circuit in the exam. So expect stuff on sources, forces, induction, and application. Something about the AC circuit. And also, one page will be a resistor circuit. That's my focus. Might tease in some of this other content as well, but that's the focus. Okay. Hope this helps. Happy studying, and I look forward to seeing you guys on Monday, and I hope I'm better by then. Or otherwise, I'll just mask up so you guys don't have to breathe my air. See you guys Monday.